Last video, we had a look at the dlmalloc implementation of free. We discovered the unlink macro that can be used to write almost arbitrary data to another address. We constructed a proof of concept heap with GDB and observed a successful write to the global offset table. But eventually we realized that our plan would not work because it contains too many null bytes and we can't write those with a strcpy. Let's quickly recap and summarize what we know about the heap and the free algorithm to refine our exploitation plan. The last video was more explorative, taking you along how you could discover the exploit yourself, but this video will be more of a presentation. This way we have two different styles of videos about the same topic, which I hope increases the amount of people who understand how it works. So let's look again how a heap chunk looks like. When you allocate a chunk of a certain size, the size of the chunk will be written to the second word and malloc will return the address here. This means you have this area for user data. The last bits of the chunk size have special meaning. Most importantly, the last bit is the previous in use bit. So that is information about the chunk before. So that's a little bit weird to wrap your head around at the beginning. This means if this block here is allocated, the block afterwards would have the last bit set, because the chunk in front of it is in use. Now a free chunk could contain more information. So once we free this chunk, we obviously can set the last bit of the chunk afterwards to 0 to indicate that the previous chunk is not in use anymore. Now imagine there is a third chunk, a chunk after the second one, which has its previous use bit not set. This means the second chunk is free. Now the algorithm would like to consolidate those two blocks. This is where the two words after the size start to become important. They are the forward and backward pointer. Just as a side note, this only applies to chunks that are bigger than the fast bin size, because fast bins are very small chunks and they don't use a double linked list. So our chunks are bigger. Let's consider this heap setup. We have a chunk we want to free, which is followed by an already free chunk. And that free chunk has two pointers, forward and backwards pointing to some other free chunks, so they are in this double linked list. Now what will happen is the free algorithm will merge these two blocks together. It will do that by first unlinking the free block from the list by using the unlink macro, and we learned what that does. It takes the forward pointer address and writes it at the forward pointer of the previous chunk, and it will take the backward pointing address and write it to the backward pointer of the next chunk. And when we obviously control the pointers of a free chunk that will be unlinked, we can point into the global offset table and write there the forward address. In the last video, we stopped here and didn't check out what happens next, but let me tell you now. So next we will increase the size of the chunk we are freeing with the size of the already free block, and then we will insert this block into the double linked list. Which means we take one chunk and look up its forward chunk and then we update the pointers accordingly to now include our chunk. This is the whole magic of the heap. Now let's get back to the famous Frag article Once Upon a Free and Voodoo Malloc Tricks to see what they tell us about the unlink exploit. Both articles contain a cool little trick to overcome the limitations of the null byte. So when we want to construct a fake chunk that we can unlink, we want to make sure that no field has to contain a null byte. This means we have to use very large values for the size. But that doesn't seem useful because the heap is not that big. But the clever ideas showed in the Frag articles make use of how computers handle negative values. So let's quickly explore what happens with a 32-bit integer value when we add a very large number. For example, FFFFFC. That would be over 4 billion. Now what happens when you add 64, which is decimal 100 to that 4 billion? That doesn't fit in 32-bit, and the carry of the addition will be lost. Now you have a very small value again. In fact, it's hex 60, which is 4 less than the 64. This means by adding 4 billion, the FFFC, to 100, we actually subtract 4. And that's a really useful behavior for our case, because this value that doesn't contain any null bytes behaves like a very small subtraction. So when we skim over the source code again, we can now make a plan. First of all, we again have to overflow the size of our chunk with a bigger value than 80. So let's do the 100 like last video. But then we could also not care about the first consolidation attempt of the previous block. This way we don't have to set up another fake chunk. So we make sure that the last bit of the block we are going to free is set to 1. So it's still in use. But we could do the consolidate forward part. There we take the next chunk and check from its next chunk the pref in use bit, and if that is not set, we attempt to unlink consolidated block. This means we need two fake blocks. One that contains the forward and backward pointer we want to use to override the GOT with an address from the heap, and the second chunk has to have a size with the lowest bit set to 0. But we can't use small size values. But if you look in the code how size is used, it's just used as an offset which is added to an address. The code doesn't check that it's a ridiculously huge chunk, it just adds the value. And here, where the trick comes into play, we could use ffffc as the size of the chunk, which results in a -4. Now think what will happen. It will take the size of that chunk, adds it to the current address to find the next chunk, which fools free into thinking the next chunk is at -4 from here. Now it will read the size of that chunk, which we could also set to ffc, which doesn't have the last bit set, and concludes, yep, the block before was not in use. Let's unlink it. And boom, it's very beautiful and clever, and doesn't contain any null bytes. So let's see if we can fill the heap in a way that we can do that with string copies. So string copies stop at null byte. This means we have to use one of them to overflow the size of the chunk we want to free with 100 hex 64. Obviously we want a pref in use bit set, so we need to overflow it with 65. This works because we don't want to override more than that. It ends in a null byte and keeps the size clean. The other string copy could be used to fill up the 100 byte until the weird conjoined fake chunks with ffc, and afterwards the two addresses we want to write. Now, like in the previous video, we will set the one address to the global offset table so that we override puts, and the other one will be pointing into the heap. This means we will redirect code execution to this heap address, and we can use the first string copy to place some shellcode here. Keep in mind that the unlink will also write some data from the global offset table to this heap area, so we have to either keep the shellcode short or jump over the smash data and continue shellcode afterwards. But we just want to call winner. So let's construct the exploit. You could do it in one line, but let me break it up to make it easier to follow. In each of these windows, we will construct one parameter, one string for each string copy. So maybe let's first take care of the string copy of the middle chunk, because that should be the one to overwrite the chunk size with 101 of the third chunk. I use echo for that, and I counted the amount of characters necessary to hit the size of the chunk, where we then write 101 hex 65. I redirected the output into a file B, and we can use it with backticks and cat as a parameter in GDB. We can then run it and investigate the heap. Looks perfect. The size of the third chunk is now hex 65. Next, let's take care of the third chunk, which is after the overflow, so it's 100 byte big. So we want to write like 100 characters to fill the chunk, and then eventually we arrive at the next chunk where we want to write the ffffcs for the trick from earlier, followed by the global offset table address and the heap address. Here I get the table address for puts and subtract -12 from it, because the heap address will be written at +12. And then comes the last string copy, the first chunk, where we want to include our shellcode to call winner. I quickly googled for an online assembler to create the shellcode. We want to call an absolute address. To do this, we have to go via a register. So we could move the address of winner into EIX and then call EIX. We can simply copy the string representation of the shellcode and write it into the file A. Cool. Now that we have all three parameters, we can rerun the program. Let's execute the free and single step into puts call. Oh, great. We follow into the heap, but somehow our shellcode is wrong. You can see that it's completely garbage. Instead of our shellcode, we have some addresses here. Oh, of course. We perform multiple frees, not just the one. We obviously write metadata over these values. But you can simply fix it by pointing to a different area of the heap. How about here at 1.4? Now we change the address and prepend some characters to our shellcode and try it again. We run it, single step into puts, and arrive at winner. Haha. Let's try it without GDB. It worked. Gosh, I love this.